Welcome you all to this UK Catalysis Hub webinar and introduce Professor Mike Bowker from Cardiff. He's Professor of Surface Science and he's going to talk to you today on the mechanism of methanol synthesis. Without further ado, I'll hand straight over to Mike.
Thank you, Josie. Welcome everybody. Welcome and good afternoon or good morning or good evening, depending where you are in the world. So the subject of this talk is methanol synthesis with some emphasis on the mechanism by which that takes place. So let's go to the next slide. Does that go? No. How do we get the next slide?
If you click on your PowerPoint, it might take you back to it.
No, I'm doing that, but it's not doing it. Is it because I've got the laser pointer? Yes, that's interesting. Didn't realize you can't use a laser pointer and change slides. Okay, so I'll use this normal pointer. So just to summarize what I want to tell you about today, I'll give you some different information, I hope, about global warming and its historical development, things you don't always hear about. And from then, after that, I'll go on to talk about methanol synthesis on the industrial types of catalysts, copper, zinc oxide, alumina, and what we know about the mechanism there. Then I'll go on to talk about some of our more recent work on alloy catalysts. And I'm going to emphasize palladium zinc. Now, palladium obviously isn't the most abundant metal, and it probably isn't one we would like to use industrially for these kinds of syntheses. But what I want to show you is that palladium zinc really is very like copper. Then the mechanism on those catalysts and its implication for the mechanism on copper, and what's more we need to do to prove that mechanism. And finally, I want to show you a couple of slides about a large-scale demonstrator methanol plant that we've been involved with that produces methanol at the rate of about 300 tons per year. Small by way of industrial standards, but very huge by way of lab standards. Okay. So it's worth remembering that every year we on the globe use about 400 years worth of plant growth that was put into the ground around 400 to 300 million years ago. That's the Carboniferous period. At that point, as you see from this graph here, at this point was when really the first seed-bearing plants developed, and probably 50 million years or so ago, the first forests evolved. They then tied up lots of CO2, and a lot of that got buried in the ground as fossil fuels. So why are we interested in hydrogen production? And a lot of what I'll talk about is related to hydrogen production and green hydrogen production. This graph shows, from a UK perspective, the relationship between increasing CO2 in the atmosphere and UK coal production early on. And of course, that followed very quickly after the invention of Watt's steam engine and other steam engines that were more efficient than the ones previously developed. And once they were developed, industrialization took off. Factories were industrialized with steam. Locomotives came along a little bit afterwards in the 1830s, 40s for train travel. And you can see that that's rather directly linked to the development of these steam engines and to coal production that was needed to drive them, the energy source for them. And linked with that then is CO2 in the atmosphere increase. So here's a slightly frightening slide. This is from Ed Hawkins at the Meteorology Department at Reading University, and shows the global rise in temperatures as a function of time from 1850 is the mean on this. I'll show that again because it's even more frightening than it looks in many ways, because if you look here, it's not really huge at this point, the increase in temperature. In fact, it doesn't really increase really fast. There is a bit of an increase there, but after 1990, 2000, you can see the CO2, the temperature rise in the atmosphere really takes off. And so we're getting very near to this 1.5 degrees C increase in temperature. So clearly we need a new kind of energy landscape, new thinking. And of course, it's not so new that we do new thinking about this, because for the last 20, 30 years, there's been more and more focus on the CO2 problem and global warming. But here's some quotes, and I can't quite see that. How do I get rid of that top bar? I don't know. So I can't read what the top one says, but anyway, this is from a novel from a long time ago. And what that says is, water, replied Harding, water decomposes its primitive elements. Water will be the coal of the future by splitting it into hydrogen and oxygen. So that was incredible prescience. That was Jules Verne in his novel, The Mysterious Island in 1874. A bit closer in time, a famous man said, I put my money on the sun and solar energy. What a source of power. I hope we don't have to wait until oil and coal run out before we tackle that. And that's Thomas Edison, the inventor of light bulbs and electrical power generation, 1931. More recently, in 2007, Al Gore and the IPCC jointly won the Nobel Peace Prize. And it was for their efforts about man-made climate change and measures needed to counteract it. But actually, although they did highlight it, they were not the first. And this chap, Guy Callender, is really not very well known. And he should be more well known. He's an very important man in the development of our ideas about global warming. But in fact, if we go even further back, Fourier, as in Fourier transforms, was very interested, as were others at the time, in the fact that the Earth was actually warmer than you might think it would be from the amount of radiation landing on it, the amount of radiation space it would give. And some people thought this was because the interior of the Earth was hot. Obviously, it's very hot. And there is some heat source from there, but actually it wasn't enough to explain the temperature difference. And so he wondered if it was something to do with heat being trapped in the atmosphere, but didn't really get any further than that. In 1861, Tyndall linked the absorbance of radiation and heat by gases in the atmosphere, gases such as carbon dioxide that they can effectively absorb infrared radiation, and may be the source of the greenhouse effect. He didn't call it the greenhouse effect at that point. An even more famous scientist, Svante Arrhenius, in 1896, used those results to estimate get some kind of idea of the sensitivity of global temperature increases to carbon dioxide, because of course this was also very important for agriculture. But at that time, there wasn't really enough data to say whether there was any effect of man-made CO2 on the atmosphere at that stage. And so it was after that, Callender in 1938, took data from a number of weather stations and specifically stated that the cause of carbon dioxide increase in the atmosphere and the global warming that he could measure from these stations was responsible for global warming. The CO2 increase was responsible for global warming. And it was known for a while as the Callender effect, but generally skepticism was around about these findings. They didn't think that man could have such a big effect on temperature in the climate. So his papers are down there at the bottom, and that you might be interested to read this very nice review, historical review by Ed Hawkins and Phil Jones. All of these are published in the Quarterly Journal of the Royal Meteorological Society. So what can we do about reducing the CO2? Well, obviously, we should make less of it, and we should use more of it if we possibly can. And there are many schemes like this in the literature. This is one by George Olah in ChemSalt Reviews for what we can do with CO2 and renewable hydrogen. The hydrogen comes from renewable energy of various forms: solar, wind, hydro, geothermal. For the UK, it's wind. There's calculations that show wind power is much more efficient for generating hydrogen than is solar photovoltaic. And then we need to get the CO2. We can take that by directly out of CO2 producing power plants or from carbon capture and storage systems. And with these two, we can then make chemicals or fuels. And the one that's the focus of my talk here is methanol. but DME is quite easily made from methanol, often within the same reactor bed. So traditionally, methanol synthesis has, well, a long time ago, Mitash, in the days of just after the ammonia synthesis developments, BASF introduced zinc oxide chromia catalysts, mainly working with CO and hydrogen to make methanol. But in the early 60s, a company in England called ICI, which no longer exists, invented the copper zinc oxide alumina process. And by using a sulfur scrubber at the front of that bed, we're able to produce methanol very efficiently in low temperature, low pressure processes. So what we're interested in is, are different catalysts possible for, in particular, CO2 hydrogenation? I'll say a little bit more about the industrial process in a minute, but obviously we'd like to make methanol from CO2 and hydrogen if we can. So what about alloys? Would copper, palladium help the reaction? Because we might imagine that palladium would enhance hydrogen dissociation compared with copper. And we might imagine that copper would reduce the ability of palladium to do methanation, for instance, or reverse water gas shift catalysis. The mechanism of methanol synthesis on these kinds of materials we looked at when I was in ICI, and we did some very simple experiments very early on, because there was a lot of dispute about whether CO or CO2 was the microscopic agent, the carbon source for making methanol. So we did some simple experiments using temperature programmed desorption on, in this case, zinc oxide. And if you look at that left panel, what that shows is CO2 adsorption after exposing to CO2 at different temperatures and fairly high pressure. It's not a UHV experiment, it's a vacuum experiment. The exposures here are 1 millibar or so. And this is mass spectrometric detection. So what you can see here is there is some kind of weakly bound form of CO2, desorbs at all temperatures, but as you increase the adsorption temperature, so a new state appears at pretty high temperature, 500 to 550. So that clearly indicates an activated adsorption of CO2 onto zinc oxide in this case. Furthermore, if you mix CO2 and hydrogen, you get four products coming off the surface: hydrogen itself and CO2, and CO and hydrogen. And also, if you dose with the product of the reaction, either formaldehyde, in this case it's formaldehyde, but also methanol, you see a fairly complex desorption pattern, but it's similar in temperature to the middle panel. So at about 580 K or so, you see a whole slew of products evolve: CO2, hydrogen, water, a little bit of dimethyl ether. You can see that signal is multiplied by 30. Methanol, which is multiplied by 10. And that coincident desorption of all those products is an indication that there is a common intermediate which is responsible for all of them. And that clearly shows CO2 is the main source of carbon. I didn't say if we adsorb CO, we don't see CO adsorption under these circumstances. So the CO can't adsorb on zinc oxide in this case. So it seems like CO2 is the main source of carbon for forming the formate intermediate. And we believe the intermediate that produces those products on the right side there is the formate. That's these products. It's the formate that's responsible for almost all of that. And it's the pivotal intermediate in methanol synthesis, at least for zinc oxide in this case. And I should mention Professor Ken Waugh. He was the senior group leader at ICI at that point, and he was a great colleague and friend and died, unfortunately, a few years ago. The formates and methoxy species have been identified now in a wide variety of surfaces, including zinc oxide. I just show you here a couple of examples of imaging such species on a surface. This is copper, in fact, copper 110. And these blobs that you can see here are individual methoxy units on the surface of a copper, well-defined copper single crystal. That's why it's so ordered, because the underlying copper is very ordered. And similarly, if you adsorb formic acid on the surface, these units here are formate species. You can, if I blow this up, you can see individual units of formate on the surface. In both these cases, it's mixed with oxygen because copper finds it quite difficult, at least in this kind of experiment, to absorb methanol or formic acid. But if you pre-dose with a bit of oxygen, then it enhances the absorption. These atoms here are oxygen atoms on the surface of the copper, and this is a different structure of oxygen atoms on the surface. But anyway, by a variety of techniques, imaging in this case and spectroscopy, we can identify methoxy and formate species. Methoxy generally decomposes at much lower temperatures than does the formate, and so the formate is more stable at reaction temperatures. So from all of that, we developed a mechanism. You can see it says a simplified potential energy reaction pathway. It's actually not very simple, is it? It's actually rather complicated. There are elements of experiment in that and elements of guesswork and intuition in that too. But basically it proceeds through this formate intermediate. There's the formate. A decomposition route makes the CO and the hydrogen. That formate can hydrogenate to biformate, as it's called, or dioxymethylene is another name for it, through to formaldehyde, methoxy, and methanol, which desorbs into the gas phase. And you can see here that the formate is the bottom of that potential well and is most likely to be rate determining in the methanol synthesis. That formate, you can see the important role here of the vacancy. So that's a crucial thing that's not in most diagrams of potential energy diagrams of methanol synthesis. That obviously, if it's on a surface like zinc oxide, as this one is here, vacancies in the presence of hydrogen are likely to play a big role in the catalysis. We'll say a bit more about this later, but you can see the vacancies are there in the presence of the formate, the hydrogenated formate, but then the vacancy is filled by the oxygen atoms from the formate when it drops an oxygen and makes the other species, single oxygen species. If we look at an industrial type catalyst, in this case, it's just methanol adsorbed, then you can see both types of formate. Unfortunately, I've not got the masses labeled here, but I think this is CO2 and hydrogen, and this is CO and hydrogen. Formate on zinc oxide, formate on copper. So again, here's a scheme for methanol synthesis. If we start at the bottom here with CO2 and hydrogen, that hydrogenates to formate. That goes through to formaldehyde by dropping an oxygen, methoxy, methanol, and finally makes methanol in the gas phase. Oxygen is included here because it very much relates to another large-scale industrial reaction. That's the selective oxidation of methanol to formaldehyde, which proceeds through co-adsorbed methanol oxygen through to formaldehyde on the surface, and then formaldehyde in the gas phase, formaldehyde and water. That's the industrial selective oxidation process to make formaldehyde. If you don't make your catalyst right, it carries on through this stream and decomposes formaldehyde to formate and CO2 and hydrogen. So under all circumstances, when you're making a methanol oxidation catalyst for selective oxidation, you've got to stop that route taking place from there to there. So one is kind of the reverse of the other. The catalyst used for selective oxidation is an iron molybdate catalyst, or sometimes silver is used too. So that's methanol oxidation. Remember, in this industrial scheme that the hydrogen source is a fossil fuel. It's methane predominantly these days, made by steam reforming, which is a hugely energetic, demanding process, extremely endothermic. You burn lots of methane outside tubes containing the catalyst to make the mix of CO, CO2 and hydrogen that you need for methanol synthesis. So here's what I consider to be the simplistic form of that scheme. Methanol is made by reacting hydrogen with CO2 to make methanol. That leaves one oxygen behind somewhere in the system, and that oxygen has to be removed. And CO removes oxygen much faster than hydrogen does. So the rate goes faster when CO is there. Now, the confusing thing about that is the sum is CO plus hydrogen makes methanol. So globally, industrially, that's the reaction. But at the microscopic level, the carbon source of methanol is CO2. Now, of course, that's not the same reaction we're interested in here. Here, we're interested in CO2 and hydrogen making methanol plus water. And I think that says 2, that should be 3 hydrogens there. It makes methanol and water. And that water is a significant player in the whole process and can lead to catalyst deactivation if the catalyst is not made in the right way. So I'd like to move on to recent work and talk about what we're trying to do with alloy catalysts. And the reason we've embarked on alloy catalysis is that we put in some grant applications in that direction to see how alloying affects a variety of catalytic reactions. So at the beginnings of the Catalyst Hub, there's then that funded some of the CO2 hydrogenation work. We then carried on through work in trying to make new routes to liquid fuels and currently we have a center-to-center grant linking Holland, Germany, and ourselves. And we also recently have initiated a Max Planck Center with the Max Planck Society in Germany. And in all these, we're working through the CO2 hydrogenation problem and trying to make both bimetallic and trimetallic alloys. So if we decided, for some reason that is now lost to my memory, we decided to start looking at not copper on zinc oxide because that was very standard, something a bit different. But let's start with palladium on zinc oxide as a base experiment and see what palladium does. So it's this CO2 hydrogenation reaction. So here are some of our first results. This was published in 2016. And if you look at the left-hand side panel, what you'll see is as much as we might expect. That is, at low temperature, when we start this reaction, having not done anything to the catalyst other than calcined it, palladium on zinc oxide is a reverse water gas shift catalyst. It converts CO2 and hydrogen into CO and water. You see there the selectivity for CO is very high at low temperatures. But then it goes down as the temperature increases and methanol goes up, which is a little surprising. However, it's to do with reduction of the catalyst in this environment. So if we look at pre-reducing the catalyst, and I think this was pre-reduced at 400 degrees centigrade, if we pre-reduce that palladium zinc oxide catalyst, lo and behold, even at low temperature, we get very good selectivity to methanol, which goes down as temperature increases because it's an exothermic reaction, and CO goes up with temperature because it's an endothermic reaction. And at higher temperatures, the methanol selectivity is really quite low. And at around this temperature, we're reaching equilibrium in methanol production too. So what is going on in this system? So if we look at XPS first, this is what happens in the XPS palladium signal, 3D signal, when we prepare the catalyst to begin with, and that's here, and we see palladium oxide, as you might expect. As we increase the temperature under reducing conditions, or rather we pre-reduce under these conditions and then look at the effect of temperature, what we can see is that the palladium oxide diminishes and makes palladium metal. But then as we go even higher in temperature, we see a new peak, and we believe this is palladium, a palladium zinc alloy. And that's confirmed by XPS measurements. If we do go through the same kind of process, what we see is after reduction at high temperatures, we shift from palladium oxide to palladium oxide to palladium metal to the alloy, palladium zinc alloy. And these are the 111 and 200 diffraction peaks. One thing that's slightly surprising about this system is we always make the beta 1-to-1 palladium zinc alloy. So equal amounts of palladium and zinc in there, and it totally dominates every kind of preparation that we've made, every variation we've made, every varying reduction temperature. And Lara Kabalan and her colleagues at the Cardiff Catalysis Institute have calculated the heat of mixing of palladium with zinc. And the reason for this dominance of the 1-to-1 appears to be the very high heat of mixing. It's got the highest heat of mixing in these calculations, about -6 EV per atom, or about 60 kilojoules per mole, 0.6 EV per atom, 60 kilojoules per mole. That compares with alloying copper with palladium with copper, for instance, is only about 0.1 to 0.2. So it's a lot. It prefers to alloy with zinc if it possibly can, if it's around in the system. So why do I say that palladium zinc is copper-like? Well, first of all, let's look at some XPS results. These, valence band spectra. These are from Nyman et al. A few years ago now, and others have found similar things for palladium when it's alloyed with all sorts of other elements. That is, when there's nothing, when it's just pure palladium, it's a D-band metal, and the D-band is at the Fermi level, and of course palladium has just about the fullest D-band in the transition metal series. When we start to add zinc to it, what you see is the D-band shifts away from the Fermi level down to 2 to 3 EV away from the Fermi level. And this looks like one of the SP metals. It looks really not so different, as you can see, from copper itself, which is shifted down from the Fermi level. Another interesting feature of palladium zinc is we find a very ordered system in transmission electron microscopy, in X-ray diffraction, and these are also calculations by Nyman's group. And what you can see, he's calculated for a roughly 1-to-1 mix of palladium with other elements, what the structure might be. Palladium gold, palladium silver, palladium copper, palladium zinc. Now, palladium zinc is rather unique in that system. For palladium gold and palladium silver, the surface is largely dominated, is segregated in the non-transition element, gold and silver. For copper, there is copper in the surface layer, but as you can see, it's rather an inhomogeneous mix. There's some disorder in that system. But when they calculate the palladium zinc system, you see it's perfectly ordered throughout, and there's no segregation to the bulk, or very little, to the surface, very little. It's a very homogeneous system. Let's see, we need to do that to get that on there. There we go. And here's another surprising result for this system. This is work carried out by Isla Gao, who is finishing her PhD very soon, and was very much involved in the palladium zinc story. The previous samples I described to you were all deposited. The palladium was deposited onto commercial zinc oxides, and they were very low areas. I think one was 6 or 8 meters squared per gram, one was about 16 meters squared per gram. So why don't we make a higher surface area zinc oxide? Presumably we'll get a much better material. But that turns out not to be the case. This is all loaded with 5% palladium. These are mostly made by CVI methods to deposit the palladium. And here we see the red circles are selectivity to methanol. The blue circles are conversion on the right curve, and the green is yield. And what you see is, if anything, there's a negative effect. But the most important point of it to me is that for a tenfold, at least tenfold increase in zinc oxide surface area, there is very little effect on the yield, on the reaction properties. It may go down by a factor of 2 roughly in conversion. We've not completed the TM of all these samples, but as far as we can tell, the palladium sample is all similar in size for these samples. That is around 3.5, 4.5 nanometers or so mean size distribution. And the implication of this kind of experiment to me and to us is that the rate largely, I've put only, but largely is perhaps a better term. It depends largely on the palladium zinc oxide interface. That is the perimeter area. And obviously, if the palladium zinc samples, particles are roughly the same size, for the 5% weight loading, they will be roughly the same number. And even though the zinc oxide area is higher, the interface perimeter will be the same. So we went on then to do some more slightly more complicated experiments to try to vary the palladium zinc ratio in a controlled kind of manner. And we did that, or rather Naomi Laws did all this work on depositing palladium and zinc by CVI methods onto titania, P25 titania, which is about 55 meters square per gram in surface area. And if we concentrate on this right-hand curve here, what you can see is when it's pure palladium, it's much as we might expect. That is, the conversion doesn't vary hugely within error across this range of varying zinc loading. It's around 8 to 9% conversion. But if we look at the product distribution, what we see is we get a lot of CO. So as we might expect, pure palladium is a reverse water gas shift catalyst. We get some methanol, about 25%, but we also make a lot of methane. We make about 30 or 30 more percent methane on the catalyst. So as we go across here, we're increasing the amount of zinc in the sample from very low loading, much less, this is molar ratio, very low loading of zinc to 2 to 1 zinc to palladium. And what you see is even at very low loading, only 1 atom in 10 in the metal, and it is all in the metal, as I'll show you in a moment, only 1 atom in 10 is in the palladium catalyst, but you can see we've dropped the methane production considerably. If we go to half the amount of zinc as palladium, it's dropped even more, and it carries on dropping to a very low level. We've also dropped the methanol synthesis. As you can see, the yellow there is the methanol. And when we get to 1-to-1, that's stoichiometric, although there's plus or minus 10% probably on that stoichiometry. You can see that the methanol is still low, and we have a lot of CO. So these are very good reverse water gas shift catalysts. As we continue going up in zinc loading, so the methanol goes up. Now we know that after 1-to-1 stoichiometry, we start to form zinc oxide on the surface of the titania. And so it's crucial to have zinc oxide around the palladium to have some methanol selectivity. By the time we get to 2-to-1, and 2-to-1 represents palladium zinc on 1 monolayer of zinc oxide on the titania catalyst. You can see that we've got dominance by methanol. We've got about 55% selectivity to methanol at that point, very little methane, and the rest is CO. So the conclusion from that is that palladium zinc is not a methanol synthesis catalyst. It's a reverse water gas shift material, and that zinc oxide must be present on the support of the catalyst for it to work to be selective to methanol. Here's some electron microscopy, and what we can see here, high resolution, high annular dark field microscopy. You can see, I can't quite see the script thing at the top of the scale, but I think this is zinc and that's palladium, could be the other way around. But the most important point is that the zinc is always associated with the palladium, even at very low molar ratios of 0.1. So zinc and palladium interact very strongly. It's likely that we get such a big effect on the methane production that at these low loadings that there is some segregation of zinc, I think, preferential segregation of zinc to the surface of the palladium. So what's our model for this reaction? Now, this is quite complicated, but let me try and lead you through it. If we look at the left-hand side of this, here's a titania with a zinc oxide layer with palladium nanoparticles on top. I've not shown the zinc in here at the moment. I'll explain what the zinc does in a moment. But the way I think this happens is a lot of people think that the role of the metal, including copper, is just as a hydrogen spillover agent. And I think I'm beginning to believe that's true. So where does the CO2 adsorb? Well, Igor Kovalech in the Cardiff Catalysis Institute and his colleagues have done many calculations, and others around the world have done them too, and find generally that CO2 binds quite weakly to palladium. So perhaps that eliminates CO2 adsorbing directly on the palladium. Much more likely is, as I showed in the earlier slides, CO2 can adsorb on zinc oxide. The zinc oxide data I showed you earlier were for a low temperature reduced zinc oxide that we believe had defects present at the surface. If we look at calculations by Richard Catlow and his colleagues, they find that it is feasible in hydrogen to make these defects. So hydrogen can spill over and make defects on the zinc oxide in the first place, and that these are amenable then to oxophilic attack by the CO2 to make some kind of CO2 intermediate, bent CO2 intermediate, probably charged with an electron from the anion vacancy that's left when water is produced from hydrogen reduction of the zinc oxide. Now, I've shown that purposely as bridging the palladium and the zinc oxide defect. I'll come back to that in a moment to discuss that further. So the CO2 fills the hole in the zinc oxide and binds to the palladium in this model. Hydrogen can then spill over onto that CO2 and make a formate in that position. And French and Richard Catalytic and their colleagues did some calculations of the conversion of CO2 to methanol to show that it was feasible in zinc oxide defects to do that process. But also it's possible that that CO2 can dissociate at the palladium surface to leave adsorbed CO and dissociated CO. We know that CO can dissociate on palladium at bridge sites. The most strongly adsorbed sites are the bridge sites on palladium, and CO can dissociate there. So some of that CO desorbs into the gas phase. That's part of the reverse water gas shift reaction. But the dissociated CO, the carbon associated with that, can be then hydrogenated to methane off the surface. So the big role here, as stated in point 5, the big role here is for zinc to passivate the palladium surface. It substitutes in the surface layer. It stops, and we've seen by infrared, and others have seen by infrared, that it stops the bridge CO forming and only allows the terminal CO, as it is also on copper terminal, and it blocks this CO dissociation, so methane formation cannot occur. I think it's not just zinc that does this role. Copper does that role too in palladium, and many other alloying metals will do the same role. And it's probably because it's simply an ensemble effect. You need at least 2 palladium atoms, probably more, together to dissociate the carbon monoxide to carbon and oxygen on the surface. And as soon as you dilute that surface with another element, it blocks that CO dissociation. So where exactly is this formate? I mean, I've proposed that this formate is here, bridging the palladium zinc particle, or maybe the copper particle and zinc oxide. That's not certain. We need more evidence to support these models. Other people claim there's just formate throughout, all over the zinc oxide, and that can be hydrogenated by spillover. But I tend to think it has got to be adjacent to the palladium zinc. It may be this form that I've shown it in, or it may be immediately adjacent to the palladium zinc nanoparticle and directly gets hydrogenated there. There's some other evidence in the literature for copper for this to be the case. And I showed you earlier the lack of dependence of or limited dependence of the synthesis rate on zinc oxide surface area that supports a perimeter model for that reaction taking place. Oh, so let me just move on to upscaling processes. And we were involved with it. This is a EU supported through their SPIRE program. It's a project called MEF-CO2, which finished a couple of years ago. And if you just put MEF-CO2 into the web, you'll find even more information about this project. It involved a lot of players STIAG, who were involved with the power plant and getting CO2 from the power plant. Other universities concerned with cleaning up that power plant gas and getting rid of the sulfur in particular, and the NOx. Hydrogenics is an electrolyzer company based in Belgium. It was responsible for the electrolyzer part of this plant. That electrolysis power could be renewable. The CO2 and hydrogen are put into a plant produced by Carbon Recycling International, CRI, which is based in Iceland. and they use, for producing hydrogen, they use geothermal power to produce their hydrogen. And this produced methanol in the end at about 250, 300 tons per year. So this is a successful collaboration. I can't say much about the catalyst that actually went into the plant in the end, but this is now been dismantled and the plant has been moved to Sweden, where it's being used to produce methanol in conjunction with a formaldehyde synthesis plant. And these kind of demonstrator systems are increasing in size all the time. And I don't believe it's going to be very long before we have a full-scale renewable hydrogen methanol synthesis process somewhere in the world. We don't need to do that. So let me conclude. Obviously, I guess everybody listening to this will know that catalytic science represents a route to a hydrogen-based economy and the route to a new kind of chemical industry, a new kind of refineries. And it's a way to reduce CO2 emissions. It's a way to fuel as well. As I said, demonstrators and bigger demonstrators are coming on stream all the time. We need more fundamental science to feed into the technological development to make new kinds of materials, catalysts that will withstand high levels of water in the stream. And we also, I've only talked here about methanol synthesis from CO2. Now, in the end, a plant will not operate with CO2 and hydrogen pure, probably. What we will do is use CO2 and hydrogen. So that being the case, we need better reverse water gas shift catalysts in front of the methanol synthesis plant that produce in the end a mix of CO2 and hydrogen, and probably do that global conversion I talked of earlier. That is a CO2 hydrogen mix, which actually works by globally CO hydrogenation and is a dry process. But also Fischer-Tropsch, we need new Fischer-Tropsch processes, a lot of work going on in that direction with CO2 and hydrogen, maybe more on methanation and a whole range of other kinds of reactions. So at that point, let me acknowledge a number of supporters for our work. Obviously, EPSRC in the UK, Engineering Physical Sciences Research Council, funds a lot of what we do. And some of that was done via the Catalysis Hub, which is based at Cardiff and a number of other UK universities, but also has an important base at the synchrotron at Harwell in Oxfordshire. Cardiff University for support, especially for the formation of the Max Planck Centre in collaboration with the Max Planck Society. Diamond Light Source for use of its facilities for electron microscopy via EPSIC and X-ray absorption spectroscopy studies, and the European Union for MEF-CO2. And let me finish by acknowledging a wide range of co-workers that have been involved in this work. I can't read them all out by name. If you're watching, you know who you are in this picture. And there's a number of others I probably haven't included, but their names are on this slide. So at that point, let me thank you for your attention and see what questions we have online.
Well, we've already got questions coming in, Mike, so I'll start reading them out. So Keith has asked, what do you think of indium oxide catalysts for this reaction?
Well, yes, indium oxide is very interesting because we've tested a wide range of materials: gallium oxide, indium oxide, zinc oxide, titania, and several others. And indium oxide is the only one that seems to make methanol without a metal co-catalyst. So we're currently working on that and modifying the surface of indium oxide. It's not as active as the metal promoted catalysts, but it's very selective. So that is rather fascinating. It's a bit worrying, of course, that indium oxide is very easily reduced to metal at quite low temperatures and is a liquid at very low temperatures. But nonetheless, it is an interesting material. It's one we will continue to pursue. And many other people around the world are looking at, with interest, at indium oxide as an active material.
And so one Fen would like to, I was asked about the purity of the methanol produced.
Purity, yes. Let me try and get the pictures on the screen. Oh, that's better. The purity, well, it's very pure except for CO. So obviously we've got a lot of reverse water gas shift, but even on standard copper catalyst, a standard copper catalyst produces a lot of CO2. In general, the methane production is low, depending on which support we use. So I think I showed 2 to 1. We've gone to very high loadings of zinc oxide versus palladium in the catalyst. Palladium on zinc oxide itself, or palladium zinc on zinc oxide, I should say, produces very little methane indeed. Palladium zinc oxide on titania also, I think, at high zinc levels is something like 0.05% methane. We get a very small amount of dimethyl ether, but very small. So it's pretty pure as far as methanol is concerned.
Okay. We have an anonymous question who suggests they might have missed the following point. What's the function of the titania when you deposit the palladium zinc over it? And
Oh, yeah.
Share the reaction conditions. Is it gas phase or liquid phase for the palladium?
Yeah, sorry, I apologies, I didn't say the conditions. The conditions for the reactor work were 20 bar and varying between 190 centigrade and 270 centigrade. We use a high throughput reactor, 16 bed reactor, and operate usually for 100 hours, all these catalysts, and they're actually remarkably stable. The role of the titania there was purely to find a higher surface area support when we started that work, on which to put the palladium zinc oxide material. So that's all. The interesting thing, of course, is that the palladium on titania alone does produce some methanol. It doesn't produce much, but it does produce some. So there may even be a 4-mate intermediate at the palladium titania interface too. Titania is reducible. It's probably not so easily reducible as zinc oxide, but it does make a little bit of CO, but a lot of methane, unfortunately.
So Mathis would like to know, do you see evidence for the palladium zinc alloying in the zinc 2P XPS region or the zinc L-edge XAS?
We've seen evidence for the zinc alloying in, even better than that is the Auger. So the Auger zinc metal peak is quite a bit shifted from the zinc oxide, zinc 2+ Auger peak. And in some of the papers I mentioned there, we report seeing the zinc metal. Having said that, all the XPS we did was after exposing the sample to air. It goes through air into the XPS machine. And so we always have zinc oxide around, even when we shouldn't. For instance, 1-to-1 palladium zinc, well, the palladium on zinc oxide itself reduced should just, no, let's get this right. Palladium zinc 1-to-1 on titania should only have zinc metal, but in XPS we always see some oxide, and it's due to oxidation in air. But we do see the zinc metal component too.
Next question is, could you expand or explain the importance of vacancies in the energy diagrams of the mechanism proposed earlier in the talk?
Right, yes, let's see. Let's move that to there. Let's escape this if I can. Oh, can I? What happens if I hit the escape button? Would that be okay?
It just goes back to your presentation, it should be fine.
Good, okay. Oh, yes,
Yeah.
right. It's much quicker to do it this way. That diagram is there.
Yeah. Right.
So the role of the vacancy is that when we did those very early experiments, we found that it was necessary to treat the zinc oxide surface first in a little mildly low temperature and a bit of hydrogen. And the role of that was to make vacancies. We could see those vacancies by detailed XPS measurements. And so that's one thing. Second thing is, it's hard to imagine, as I said, CO2 calculations for palladium indicate it adsorbs very weakly. When we use the not reduced zinc oxide, we can't get these high temperature states in TPD. I think it's pretty easy to imagine that we have vacancies in the zinc oxide lattice, which will be probably either small polarons or large polarons that either contain 1 electron or 2 electrons left behind by loss of the neutral oxygen. It's easy to imagine, I think, that that's oxophilic. It wants to pull in the CO2 and grab that oxygen off the CO2 if it possibly can. So those are all the kinds of reasons we put the vacancy in there. We have calculations. As I said, Richard Catlow has done calculations on the energy of vacancies on zinc oxide. And we did some calculations in ICI. I didn't mention it. I should have. A guy called Bill McCroat, who's no longer with us, who was a very important theorist in ICI, who did calculations on heats of formation of vacancies on zinc oxide. And so part of the input to this diagram is partly from him.
So the next question starts with thanks for the lovely talk. What is the advantage if you compare the palladium zinc with a copper zinc oxide alumina system?
Yeah, that's the question we don't really want to hear, but let me try and answer it. This began experimentally, obviously, and academically in trying to understand alloying and its effect on methanol synthesis. We were very surprised first when we found that palladium alloyed with zinc. We were also happily surprised to find that that was a very selective kind of material. So that came as a big surprise to us. Now, obviously, although the loadings are much lower than in a copper catalyst, here we typically use 5% palladium, but we can use as low as 1% palladium. That is still a very expensive system to make commercially. Number one, it's a very expensive system to make for the globe environmentally. It's not an earth abundant metal. So practically, we probably wouldn't want to use it unless there's some astonishing finding we make about improved performance. Compared with the industrial copper zinc oxide alumina catalyst, as far as we can tell, per surface atom of copper and palladium, for equivalent surface atoms, the rate is the same, roughly the same. But that's at 5% loading of palladium. But for a roughly 50% copper loading CZA catalyst, the copper catalyst is much better. It reaches equilibrium quicker than the palladium type of catalysts do. So I don't think this is really practically applicable. The only thing I would say in terms of practice is that we have tested these catalysts industrially in an industrial environment, and they are very, very stable. And if anything, more stable than CZA catalysts in a water environment. I hope that answers your question.
So the next question is it difficult to manage the production of gas expanding to increase pressure large scale?
Let's get this right. Well, there's a reduction in pressure in synthesis because we go from 4 molecules to 2. So I'm not sure if that's the angle we're talking about here. So there isn't an increase in pressure in synthesis. There's something of a decrease. Industrially, I believe the equilibrium conversions are somewhere around 15%. They're recycle plants. So, of course, the drop in pressure is not absolutely massive in these systems.
And the final question to come in so far, so if you've got any more questions, type quickly. Can we use silica porous materials for this reaction as a catalyst?
We've certainly made catalysts on ZSM5. I'm not sure we actually got the active material, that is either copper zinc. We made copper zinc catalysts on ZSM5. We also made palladium zinc catalysts on ZSM5 and varied the acidity of the zeolite. So the interest there, of course, is making dimethyl ether, and they do give good yields of dimethyl ether, those kinds of materials. In those cases, I believe the metal particles were all on the exterior of the pore system. So yes, mesoporous materials could be of more interest. We've not delved into that so far, but that could be an interesting direction to go with these kinds of experiments. Thank you.
I will take Chair's privilege and to ask a final question if you have time, Mike.
Yes, sure.
I thought the pilot plant you had with the MEFCO project was really interesting, and you spoke about the fact that probably you'd need a slightly different feedstock in reality. what other barriers do you think there are towards implementation of this kind of system?
Economics. Now, that project started now probably about 8 years ago. By the time we finished that project, there was a group from Milan involved who were doing the economic calculations of whether it is better to use wind power to generate the electricity. The big cost, by the way, in these plants is the electrolyzer. The electrolyzers, I've forgotten the percent, 70% of the cost of the whole plant. But wind energy was shown to be the best, most efficient way of making it. And that calculation also showed that if we went from the original 500 tons a year, was the original design specification, to 50,000 tons of a year, it went from loss making to profit making. Now that was at that time when fossil fuel prices were lower than they are now. So I believe the economics are shifting very much in this direction.
Okay. The one last question I snuck in. David Gerardo was asking about the role of the aluminium in the copper zinc alumina systems.
Yeah, that is always a bit of a mystery because I believe there is some zinc aluminate in there. So some of the zinc oxide reacts directly with the alumina to make zinc aluminate. But also I think the main role of that then is a stabilizing agent. Often when alumina is in catalysts, it's because it's a very refractory material. It helps stop sintering of the material with time. So I'd say the main role of alumina, which is a minor component in these catalysts, is one of stabilization of the particle size of the copper during life on stream. And they're on stream for quite a long time, years, you know. So that's the main role.
Okay. Well, thank you very much, Mike, for a fascinating talk. I think you can tell from the sheer number of questions how interesting it was to everyone. So thank you very much. If you didn't catch the whole talk, it will go up on our YouTube page. Check out the Cat Hub website details. We have a webinar coming up. Karina's put the webinars in the link in the chat. So the next webinar is on the 9th of May. And it's about the future of XFEL in chemical sciences. So that'll be a really interesting discussion of plans for possibly UK XFEL or other initiatives that might be really beneficial to chemical sciences. So do join us then. And then towards the end of the May, we have a talk by Rosa Arago. So check out the website for all the details of that. And thank you very much for joining us. I hope to see you again soon. Thanks, Mike.
Thank you, Josie, and thank you, everybody.